How's it going, everybody? In this particular video, we're going to start off with a high-level overview of switching. And mainly the point that I'm trying to get across and to go through is make sure that everybody understands what a switch does. And, if you're here, you may not be studying for the exam, which is fine. Yeah, it's up to you. But where I'm really pointing this towards is, do you understand how a switch operates? There are some things that need to be understood, and so we're going to take a look at that right now. So what I'm going to do is I'm going to go ahead and bring over paint. I'm going to draw some stuff out for you guys. So this kind of does assume that you have a foundational level of understanding when it comes to switching, and if you don't, you're about to get one. So the way this works out here, we're going to just have a regular switch. I'm just going to draw some stuff here. Then we're going to have a host here. We're going to have a host here, and this guy is just going to hang out on the network. We're going to have a host over here. Let's do it on this side. We're going to have a host here, and he's doing the same thing. He's just hanging out on the network, having a good old time. We're going to have a connection here that connects over to another switch, and then we're going to connect to a router. And that router is going to connect off to whatever it may connect off to. So you got this guy connecting here, you got this guy connecting here. Then we're going to have another guy connecting off of this guy. This guy is having a wonderful day as well on the network. So everybody's all smiles, right? Well, the way this is going to work out here, let's say this is host 1, this is host 2, and this is host 3. Doesn't matter what they are, they're just the host of the network. And the reason I say it doesn't matter is because whether you are a server, whether you are a laptop, whether you are a printer, an access point, you are all nodes on a network. You all have a MAC address, you all have an IP address. You are reachable, that is what matters. So what a switch is going to do, a couple of things is going to happen. So by default, you turn the computer on in the morning and then this port lights up, right? Well, what ends up happening is that port comes up and there's going to be a lot of chatter. There's going to be chatter going this way. There's going to be chatter going that way. There's just chatter. Networks are noisy. If you were to look at a Wireshark capture, you would see what I mean. So what ends up happening is whatever this guy's MAC address is, this is the MAC address that's physically burned in on that port level. So if you were to do a show or do an IP config / all and that physical address, that's going to be what this guy's going to learn in. So what the switch is going to do is he's going to build a table of MAC addresses based off of where that MAC address is learned. So let's say this is port 1, this is port 2. I know that's not an actual situation. It would be more like this if this was a switch here and this was a switch here. Let's say that this would be port 1 here, this would be port 2, this would be port 3, this would be port 4, etc. You'd have odd on top, you'd have even on the bottom, right? So that's actually not, this example here isn't exactly true to what you'd see on the physical, the lineup on the ports, but it's close enough. So what the switch is going to do is it's going to say, okay, I've got host 1 on port 1 with a MAC address of A. Okay, and then I've got this is on port 1. On port 2, I have host B, so I have MAC address B sitting here. Okay, so now they've learned the switch has learned the MAC address that the hosts have advertised to the switch, and the switch has associated the port that it learned that MAC address on to that MAC address. So the point being here is, let's say this guy here is 10.1.1.20, and this guy over here is 10.1.1.10. Actually, let me switch over to my pen. It's a little easier to write with. So I don't know why my pen gets a little weird every now and then. It won't actually. Anywho, you guys probably don't care. That's all right though. So if I'm 10.1.1.10 and this guy over here is 10.1.1.20, and I want to ping from here to here, What is going to be needed to happen in order for that to work? Do I need to, and if you're watching this video, you can comment if you'd like. But what's going to end up happening here is, and this is my first question, do I need to route via IP? Oh, and I should preface these are /24 networks. So do I need to route in between the hosts in order to get to from host 1 to host 2? No, they're on the same network. So just go back to basic subnetting. They're on the same subnet. So what does host 1 need to know in order to get to host, or host 1 need to get to host 2? What is needed? Any ideas? I'm making you think about it. Okay, I'll give you the answer. Host 1 needs to know the destination MAC address of host B, or host 2 in this case. So what's going to end up happening here is host 1 knows its MAC address, and that happens to be A. Although it doesn't know the MAC address of host 2, which is B in this case, right here. So what ends up happening here is the host here, because his local ARP table, if you type in on Mac, or I'm sorry, on Windows, ARP space -A, you'll see what MAC addresses you know about, and the associated IP address that goes along with them. So what he's going to do instead is he's going to ARP out and say, hey, I want to talk to 10.1.1.20, but I don't know the MAC address of 10.1.1.20. So the switch receives that ARP in, and now ARPs are local to the VLAN. So let's say this is VLAN 1, considering the third octet is, it's a 1. So what's going to end up happening is an ARP is going to be sent out every interface, so this interface as well as this interface right here. And what's going to end up happening is the switch is going to say, okay, I need to know who owns the MAC address for 10.1.1.20. Well, host 2 gets that and says, well, wait a minute, I've got 10.1.1.20. And I have MAC address B on my network. So I'm going to go ahead and I'm going to return that back in. That is how the MAC address table, or the CAM table, the content addressable memory, that is how that is populated. So once the MAC address table is built, then we can go ahead to the next step, and we can go ahead and on host 1 side, we can say the source is going to be A, or let's do this. The source will be MAC A, and the destination will be MAC B. So then I build my layer 2 header with the source and destination MAC address. So what ends up happening is the ping comes in on the switch port. The switch looks at the destination MAC address and says, oh, you're trying to get to host B, or I'm sorry, host 2 that has a MAC address of B, and I learned the MAC address of B off of port 2 to get to host 2, and then therefore I'm going to route you, or switch you, I should say, from port 1 to port 2. And that's basically how the switching process works. So that is going to work from there. Now, what happens if I'm trying to get to host 3? Let's say this guy is 10.1.1.30. So this is /24. Now what needs to happen? And right now, if we look at this, actually let me do this real quick. I'm going to put host 3 in here. But right at the moment, we don't know his MAC address. So we are 10.1.1.30, and we need to know we need to figure out his MAC address. Well, he's connected to, this is switch 1, this is switch 2, this is router 1 in case anybody cared. Well, here's the thing that's going to end up happening. If host 1 wants to talk to host 3, and right now we don't have the MAC address table built in order to receive that. What's going to end up happening now is host 1 is going to do the exact same thing he just did for reachability to host 2. He's going to ARP for that. Now remember, ARP goes out every interface in that VLAN. So we're still in VLAN 1. So that means that the ARP is going to go this way and this way. Well, this guy's going to say, well, that's not me, I'm going to drop the ARP. But what I'm going to do is, because it's going to go across the link, the ARP is going to traverse the trunk between switch 1 and switch 2. Switch 2 is going to get that and send the ARP out to this interface and this interface. And then, because the layer 3 header, the layer 3 header is going to consist of the IP address of 10.1.1.10 as the source, and the destination is 10.1.1.20, or I'm sorry, 30 as the destination. So you have that in play. Now, because of this situation, you and if, in case anybody was wondering, the source, so the layer 2 header, the source address is going to be A. The destination is going to be all F's because it's a broadcast. He doesn't know what it is. So host 1 says, I don't know what it is. I'm just going to send it out as all F's. So he sends it out as all F's, and then when he gets it back, because it goes out as a broadcast, the same thing that DHCP would do. He gets, host 3 gets it and says, well, wait a minute, I have the IP address of 10.1.1.30. So I'm going to respond back with a unicast reply that says what? What is host 3 going to send back to host 1? Well, what he's going to do is he's going to rewrite the layer 2 header, right? He's going to come back up here and he's going to say, well, switch 2 learned on port 3 that I have MAC address C, right? What I'm also going to, on this is port 3 here in this case. What I learned on port, say, 24 is that I learned, this would be port 24, or I'm sorry, yeah, we'll say a 24, actually, let's do this guy. This will be host, and we'll say this is port 1, this is port 2, this is port 24. And then this is 3, and this is, eventually will be C. Here he'll learn port 3, or host 3, MAC address C on port 3. He's going to learn port 24, he's going to learn host 1 of MAC address A. And on port 24, he's going to learn host 2 of MAC address B. Okay? So what he's going to end up doing now is he's going to take that information and he's going to send a message back across the trunk link to this guy. And so what's going to end up happening is you're going to say 3 is attached to C. So in order to get the host 3, I need to utilize the MAC address of C, which I learned on port 24. So in order for him to ping, he needs to come in on this interface. I'm going to change my color real quick over to red. He's going to come in on this interface here, and then he's going to get switched down to here on port 24 in this case. He goes across the trunk, switch 2 receives it, and says, okay, well, I came in, received the traffic in from host 1, going to host 3, I need to make that port go out on port 3. Host 3 gets it and says, oh, I have a type 8 code, type 8 code 0 ICMP. Basically, it's a ping request. And then I'm going to send a ping reply with the type 0 code 0 back out, and then you're going to see the message come back in, go to host 1, and that's going to be how this works out. Now, the MAC address table does have a default timer value of, anybody want to take a stab at what it is? 300 seconds. 5 whole minutes. Not very long. It is manipulable. So we're going to take a look at how that would work. So that is basically the way that would break down. So that is a switching, basically what a switch is designed to do. So it builds the CAM table. Now, let me ask this question. What happens if the CAM table or the MAC address table is full? Let's say that the MAC address table of this switch can hold 1,024 MAC addresses in its table. What does it do when it learns, +1? Any ideas? Well, unlike a former instructor of mine, it does not blow up and stop working. Totally not the right answer. It does not do that. What it actually will do is it will go back to a hub-like behavior. What it will do is it will just start sending traffic out everywhere. Now remember, a hub, traffic would come in on a hub interface, and all these interfaces I just drew here, if the traffic came in on here, the traffic would be sent out every interface on this hub, because a hub is just a layer 1 repeater. It just sends the information out. It doesn't know any better. What it won't do is it won't send the ARP out or the message out the interface it received it in on because it just received it. Because you're tying that interface up. What will end up happening is anything that's connected on any of these links will receive that information, and then if it's not addressed to it when it starts to decapsulate the packet, it'll just drop it. And it'll say, you know what, it's not for me, I don't care. Where a switch intelligently moves the traffic between interfaces. So I'm going to look at my layer 3, basically my layer 2 routing table, if you will. And that's what the reason I say that is because layer 3 routing works the exact same way. So the MAC address table is a way for you to figure out where you forward based off of the MAC address. Routing table forwards based off of the layer 3 header, which is the IP. The difference between the two, which basically is just which header it forwards based off of. In this case here, you're forwarding off the layer 2 header. In an IP routing table, you're routing based off the layer 3. Now, the only major difference between the two is I'm going to come in on a layer 3 interface, and the router is immediately going to strip off the layer 2 header. What he'll then do is he'll decapsulate the layer 3. When he gets to the layer 3 destination IP address, he's going to look at his local interfaces and say, okay, does that match? Basically, it's saying, is the packet destined for me? If it's 10.1.1.1, then you may have been trying to telnet to that particular device. So when you telnet to something like my home switch or my home router or my home access point, the destination IP address is the IP address of that box, so it knows to answer the request. If the destination IP address is not the local address configured on any of the interfaces, it knows to look in the routing table. Okay, where am I sending this traffic? Where am I trying to go? It looks in the layer 3 routing table. The routing table has a match that'll say, okay, great. Which interface do I use to get there? The same thing occurs right here. If I know that I'm trying to get to MAC address C, I learned that on port 24. So that means I had to switch the traffic from port 1 to port 24 in order for it to go across the trunk link to get to switch 2. The same occurrence happens in a router. If I have traffic coming in on this interface, which is fast 0/1, and then I have an interface over here, which is fast 0/0, so this is my inside, this is my outside. What will end up happening is traffic comes in on this interface, the layer 2 header is ripped off, I look at the layer 3 destination IP, I look in the routing table, and this guy is 8888, and I happen to have a default route sitting in my routing table. That is going to be the shortest match possible, and it's saying to point out towards fast 0/0. So what I'm going to do is I'm going to say, okay, if I don't have a longer match, if I don't have a /1 or greater, I am simply going to take that information right there. I'm going to route it based off this default route that I have right here, pointing out fast 0/0. All I'm going to do then is it's likely that it's being natted. So what I'm going to do is I'm going to switch it from this interface to this interface. The same thing happens between port 1 and port 24, from switch 1 to switch 2, for host 1 to talk to host 3. I come over here, I switch the packet between the interfaces. I rewrite the layer 2 header so that this guy is a source and the destination is whatever the next stop IP address is. And then I NAT it from whatever the local addresses say, 172.16.10.12, and then all I do, come over here and change that over to 91.22.63.13. Maybe that's my public IP. So I NAT it from this as the inside source local address to the outside source local address, and then I NAT it over to this so that when Google when you try to ping Google, it appears the traffic is coming from the 91.22.63.13 IP and not 172.16.10.12. So you NAT it that way, and there's a state table that's built inside the NAT table, kind of like an ASA would do. And then when the ping reply goes out, or I'm sorry, ping request goes out, the ping reply is going to have a state that it'll be able to listen for. He comes back in, on this interface, he's natted back to 172.16.10.12, and then the initiating host receives the ping. So routing and switching have a lot in common. As you can see, switching will simply switch based off the MAC address. A router will look at the layer 2 header, rip it off, then look at the destination IP address, see if that packet is destined for itself. If not, let's check the routing table. Now, what happens if there's no route in the routing table? Well, what happens if you don't know where you're going? You don't know where you're going, so you have to drop the packet. Now, there might be some sort of special circumstance in here where there may not be a more specific route specifically, but you might be doing something like policy-based routing, where you're saying anything that might be going, that might be ping, or might be going to Google, send out this tunnel over here that you have configured. So you would policy route and set the next hop IP, set IP next hop to be X, and that would forward it out here. So you don't, in traditional routing, you would need a destination IP address to map towards, or at least something that could potentially get you where you want to go. A default route, whether it is sourced from the internet or whether it is redistributed into the routing protocol or whatever, it really doesn't make much of a difference. As long as you have a way of getting the traffic from where it's at to where it needs to go, the last device that is used in the forwarding path to the destination, that device will ultimately determine where the traffic goes. And eventually you might hit a roadblock where there is no other match and the packet gets dropped. Because remember, when you're dealing with switching, these are layer 2 and they're transparent. So if I was to look at a regular environment, my switching environment should be completely should not show up at all to my end users. It's just a way for them to get from where they're at to the router. So switches allow you to take that single interface on a router, like this guy right here, and it allows you to basically multiplex it. Switches are just a great way for you to add port density where you need it. And that's all a switch really does. And then because of the fact of its capabilities, I mean, it does a lot more than that, but that's its general purpose. Instead of having just one connection, so like for instance, instead of me connecting one computer to this interface, I can connect a 48 port switch to it, and I can give 47 different computers access to the same network, potentially the same internet connection. So it really depends on where you're trying to go with it. And that, at the end of the day, is what a switch does, and that is how a router operates. If you understand that part, you're in really, really good shape. So, with that being said, that is a high-level overview of switching. That is the really important part. So I'm not going to go into details of how to map VLANs to ports or how trunking works. I will cover those in separate videos, in separate setups. One of the things that I'm going to let you guys know, I'll be bouncing between hardware and software devices. So I have a 3550 that I'll be utilizing to show things like, for instance, let me go ahead and pull up Secure CRT. If I click right here on this home switch, this is my home switch that switches my home network. If I do a show SDM prefer, and I do get the interface, this is going to be that SDM thing that is set up. So right now it's in the default template mode, which basically means it's just running in VLAN mode. So this basically optimize the resources in the switch to support this level of features for 8 router interfaces and 1,000 VLANs. So really not that big. If I was to go over to Unicast Routing, I would be able to handle up to 8,000 MAC addresses. So so the number of Unicast MAC addresses I can handle is 5,000. If I change this over to Unicast Routing, I can handle up to 8,000. Or I'm sorry, 8,000 routes. Security access control entries would be 1,000, so on and so forth. So I'd be able to do a lot with that. So number of Unicast MAC addresses I can hold is 5,000. I can hold 1,000 VLANs. So I do show VLAN brief. Right now I've got a bunch of different stuff configured. but none of it's really working. So there's a lot of testing and stuff in here that I've done. I'm all in VLAN 1. I really don't care about it because it's a home network. I could split things off if I was so inclined. If I do a show IP route, I don't think I have layer 3. Oh, I do have route. It is a layer 3 switch. It does have the EMI image. So show version pipe include iOS. It does have the EMI image on it. So that was one of the things that I made sure of. And basically, the 3550 was originally purchased for the CCA version 4 exam. So that is what's going on. So I hope this was informative for everybody. And as we go further, we'll dig into this in more and more detail. Like I said, if there's anything in the switch blueprint that you would like me to touch on, leave a comment in the below, and I will be more than happy to take a look at it. Now, granted, don't ask for some off the wall, and I'm not going to go through and show you guys how to set up an identity services engine like ICE or anything like that. If it's a relatively straightforward optimization or something like that, I'll come up with something and be able to work with it just to demo it so you guys can see what it would look like, and go from there. And we're gonna be doing a lot here, so just bear with me. I'm releasing the videos as I record them instead of holding them up in blocks and then releasing these one fell swoop so that people can maximize their time. So I can fit a video here and a video here and just be done with it. So until next time, guys, thanks for watching. I hope this was informative for you, and I would like to thank you for viewing.